Started now. By the way, I'm going to be starting to kind of go back to my system of taking breaks for about 5 or 10 minutes in the middle of our classes. That's partially just for my benefit. This is actually kind of challenging for me to teach like this. So if I take a 5-minute break or a 10-minute break in the middle, it'll probably do me some good. So don't be surprised if I do that. Also, I am recording these Zoom lectures, as you know, so I will post the video of this when we're all done. And so you can always go back and watch it again, or if you can't stay throughout the entire time, don't worry, you'll be able to pick up on the stuff that you missed. I also have a lot of video for this material that's coming up in chapters 7 and chapters 8 especially. So I'm going to be sending you guys the links to some of those videos as well. So there'll be no lack of resources for you guys to have to look at, because I know this is not ideal to do things in this fashion. So here's what we're going to do today. I'm going to spend the first part of our time talking about chapter 7. This is the chapter on eigenvalues and eigenvectors. No discussion of linear algebra could ever be satisfactory without talking about eigenvalues and eigenvectors. So we're going to do that first. Then, as I said, we'll take a break. And then later in the class, I'm going to go over some questions that you might have from the homework that's due tonight, as well as a group work that is based on the material from chapter 6. Remember that sections 6.3 and 6.4, you were supposed to watch videos for. And so I'm going to be assuming that you've kind of done that already, and we're going to practice a little bit with that as well as practicing on the homework. Okay, does anybody have any logistical questions before we get started? Okay, I guess I explained everything. So let's go ahead and get started. We're going to jump in to chapter 7, and I'm going to kind of take it from the top. I know that I had asked you to watch maybe 20 minutes of a video on it, but there's no real harm in having me just kind of recap that very first part of chapter 7 with you. So let me see if I can get started here on my board, and let me know if you can't see what I'm writing. So this is chapter 7, and this is going to be about eigenvalues and eigenvectors. I am going to move this chair out of my way, actually, so just give me a second here. It's in my way a little bit too much. Okay, so eigenvalues and eigenvectors. This is the topic for chapter 7. Throughout this chapter, guys, all of our matrices are going to be square size. So capital A is going to be an n by n matrix. Okay, so we'll always have a square matrix when we're talking about eigenvalues and eigenvectors. And pull this just a little closer for you. Okay, that might be a little bit better, easier to see that. Okay, so we're going to look at square matrices. Now, you might remember from chapter 6 that any matrix can be associated with a linear transformation from Rn to Rm, right? In this case, of course, that transformation would go from Rn to Rn because the matrix is a square size. So what we can actually do is we can consider the following thing. We can take our matrix A and we can imagine multiplying it by a vector. Now this vector would be in Rn. So we could take a vector in Rn there, and it might be the case that after we take the matrix and we multiply by this vector, by the way, the vector v should be drawn as a column. So you've got a square matrix, and then you're right multiplying by a column, an n by 1 column, which is a vector in Rn. It could be that after you do that multiplication, you get a multiple, which is called lambda, a multiple lambda of the same vector v back again. Okay, so guys, what's on the board behind me right now is the most important equation in chapter 7. Okay, I'm going straight to the point here. So this is the eigenvalue eigenvector equation. So if this happens, if v is not 0, then we call v an eigenvector. Now I will usually abbreviate that as E vector. So an eigenvector, and the lambda, which could be any real number, by the way. Lambda is just a scalar, right? I should have said that here. Lambda is just an element of the real numbers. So lambda is a scalar, and this is called an eigenvalue. We call lambda an eigenvalue. Okay, I'm going to do an example in just a minute, but of course feel welcome to unmute yourself and ask a question at any point, okay? And sometimes we kind of put the eigenvalues and eigenvectors together, and we'll do something like this. We'll put kind of like a pair here. So I'll usually put the eigenvalue lambda first, and then put the vector v after that. This is just called an eigen pair. So an eigen pair is just a scalar lambda put together with a corresponding eigenvector v. So we can pair these things up, right? We can match up the lambdas with the v's. So lambda and v. So these are the eigenvalue eigenvector pairs. Eigenvalues and eigenvectors are extremely important in applications of linear algebra. For instance, in the world of computer graphics, eigenvalues and eigenvectors play a big role in sort of how images that are on a computer graphics display, right, on a monitor of some kind, how those images behave if you rotate or flip or sort of do different operations sort of geometrically with what's on that monitor. So eigenvalues and eigenvectors can help computer scientists to sort of understand, like, physically and visually what's going to happen if certain operations are applied to an image that's on a screen. And eigenvalues and eigenvectors are very important in statistics as well, in modeling long-term repetitive behaviors of things that could happen. Suppose you have two professors and you have students that are switching back and forth between those two professors' classes. Say every day, certain fraction of the students go this way and a certain fraction go that way, right? We can ask, well, at the end of the semester, right, how will the students be distributed among those two professors? This is completely solvable using the theory of eigenvalues and eigenvectors. So this is a big deal, right? And we're going to spend basically this week, at the most just today and Thursday, talking about this topic here in chapter 7. So the equation in the box is extremely important for understanding the theory of eigenvalues and eigenvectors. As you know, I like to ask theoretical questions as well as computational questions. It turns out that this boxed equation up here is not so handy for understanding how to do the computations, okay? It doesn't really solve the problems for us. So I'm going to go into how we do the computations now, but it's very easy to forget about this box equation, and I don't want you to forget about it. So we're going to have some theoretical examples later that force us to come back to this box again. And actually, the homework that you're going to be doing for Thursday will involve some of the theoretical applications of eigenvalues and eigenvectors, which that box has a lot to do with, okay? But the computational part of this is going to come when we start looking at the following question. How do we find these eigenpairs? how do we find these eigenpairs? Like, you know, I could give you an easy enough example, right? I could make something up. I could say, you know, let's let A be the matrix. Okay, so let's suppose I have 6, -4, 0, and 4, right? And what I can do is I can give you a proposed vector to look at. So let me just do that right here. Let me look at the vector V equal to, let's say, 2 and 1, like that. So I can do that, and then I can say, all right, let me calculate A times V. So if I do that, here's A. It's just the matrix, 2 by 2 matrix right here. I put down A, and then I put down V. And when you multiply this out, just using your, so you're just going to do your usual matrix multiplication here, guys. When you multiply this out, what you get is 8 and 4. Right? So you basically started with the vector 2, 1, and you ended up with the vector 8, 4, and that is just 4 times V. That is just 4 times the original vector, right? It's just basically what's happened. What's happened is, so you have this eigenpair, which would be 4, 2, and 1. Right? What's basically happened is you have this vector, I'll call it V right here, and it's just getting stretched by a factor of 4. So eigenvalues and eigenvectors involve stretching. You're not turning the vectors, you're just scalar multiplying the vector by some scalar lambda. So on this problem, lambda was 4. And so the V got stretched by a factor of 4. But your question that you're going to ask me is going to be, well, how did you know that 2, 1 was an eigenvector for that matrix, right? It's like I pulled it out of thin air. So we need to have a procedure for finding the eigenvalues and eigenvectors, and that's what I want to explain right here. It's in that video that you guys hopefully watched already, but I'm just going to very quickly remind you how this works, okay? Are there any questions so far? Okay, great. Everybody can read this so far, so good it looks like. All right, so let's go ahead and I'm going to talk about how we actually find the eigenvalues and eigenvectors if they are not just handed to us. Okay, so here's what we're going to do. We're going to take that original equation, AV equals lambda V, and I'm going to subtract everything to the left side. Okay, so I'm going to do a series of steps over here on the left side of my board right now. Now, when you look at that second equation, AV minus lambda V equals 0, you might want to factor out the lambda. I'm sorry, you might want to factor out the V. Right? So I can do that. So I'm going to leave my 0 over here. I'm going to put my V right here. Now the thing is, when you factor the V out of this, you have capital A minus, and there you have a lambda, you see? Now, what I've written there, guys, right now on that last line does not make sense because I'm taking a matrix and I'm subtracting a number from that. You can't do that, right? You can't take a matrix and subtract a number. So what we're going to do is we're going to harmlessly slip in here an identity matrix. Okay, so the identity matrix, of course, that's the matrix that's just got ones going down the main diagonal, right? And if you take the identity matrix times anything, it doesn't change what that other thing is. So, you know, this is a harmless thing to add right here. Okay. Now, what this equation is saying is that if we take this matrix A minus lambda I and multiply it by V, we get 0. That just means that V is in the null space, right, of the matrix that I circled, right? So this is just saying that V is an element of the null space of A minus lambda I. So when we're trying to find the eigenvectors, the V's that we're talking about right here, when we're trying to find those eigenvectors, we're going to be doing a null space calculation. So we're going to have to find the null space of a matrix again. Now remember that I mentioned that an eigenvector has to be non-zero. This is just a definition. The definition of an eigenvector is that it's a non-zero vector such that AV equals lambda V. Okay? So what we're saying in this last line right here is that there is a non-zero vector in the null space of A minus lambda I, right? Well, that means that the matrix A minus lambda I, if you think about it, if you go back, remember it's a square matrix, it's not invertible, right? Remember that I know it's been a long spring break, but one of the things that we learned back in chapter 4 is that an invertible matrix has a null space of 0, right? Has a nullity of 0. So this matrix that we are looking at right here, A minus lambda I, does not have a null space of 0, which means that that matrix is not invertible. So let me write that down as the next line here. A minus lambda I is not invertible. This is very important, because if the matrix is not invertible, then you probably remember lots of things about this matrix, right? One of them is that the determinant of this matrix, if it's not invertible, the determinant of that matrix must be 0, right? So let's put that down. The determinant of A minus lambda I must be 0. That's exactly right. And this is called the characteristic equation. So let me write that down as well while I'm here. The characteristic equation for capital A. So when I say it's an equation, when I say that that's an equation, what I mean, of course, is that there's going to be lambdas in it, right? Take a look. There's lambdas that have been subtracted off of the main diagonal of A. We're going to practice this in just a second, but this is the whole idea, right? So you're going to be trying to solve the characteristic equation for those lambdas, those lambda values, right? So that's how you find the eigenvalues. You find the eigenvalues by solving this boxed equation, this characteristic equation for lambda. And you find the eigenvectors by finding the null spaces of those corresponding A minus lambda I. So you usually will find the lambdas first and then find the V's. Okay? Let us practice that procedure on the example at the right. Let's suppose I didn't tell you ahead of time what the eigenvectors and eigenvalues were. Let's go back to this example and practice this theory that I've just outlined here on the right side of the board. Okay? So here's an example. Find, oh, before I go on, one other important thing here, guys. This null space, right? It is a subspace of Rn. Remember that? It's actually called, my notation is going to be E sub lambda, and this is called an Eigenspace. So an Eigenspace is just a subspace of Rn that corresponds to the collection of the eigenvectors that correspond to lambda. So every eigenvalue has a corresponding eigenspace. Does this make sense? So if I find a lambda value, then I can go through and figure out, well, what are all of the eigenvectors that go with that lambda? They're going to form an eigenspace because they are the null space of this matrix. Okay? And because they are subspaces, right? Because these belong inside of Rn as subspaces, then we can ask for a basis for these eigenspaces. And that's what I'm going to recommend that you try to do on the homework. I think some of the instructions for the homework that you're going to be doing later on for Thursday and for next week, I think they say things like find the eigenvectors of the matrix. The best thing to do is actually to just find a basis for the eigenspaces. So I'm going to do that right here. So find bases. Here's my example. Find bases for the eigenspaces of the matrix A, which is the same matrix again, 6, -4, 0, and 4. Okay, so we're going to take, this is the same matrix that we wrote down a few minutes ago, and I just threw out what the eigenvector was that we were going to work with. Let's see if we could derive it now. Okay, the first step is to find the corresponding lambdas, to find the eigenvalues. So the solution, here we go. I'm going to write down the determinant of, now what matrix am I going to look at? It's this matrix right here, A minus lambda I. I don't know what lambda is yet, so I'm just going to subtract lambda off of the main diagonal of this matrix. So it's going to look something like this. Okay? Something like that. Now, this is just a little 2 by 2 determinant, so I can use my little 2 by 2 determinant formula, you know, AD minus BC that we learned back in the determinant chapter 3. So this is just going to be 6 minus lambda times 4 minus lambda minus nothing, right? Because there's a 0 there in the lower left corner. Okay, so this is what we have. And what I'm going to do is I'm going to cheat here a little bit. This is a minus sign, but I'm going to change this to an equal and write the word set there. So I am going to set this determinant equal to 0, exactly according to this box formula over here. And the minute that you do that, you've already got a nice factored expression. You can see that lambda is equal to 6 or lambda is equal to 4. These are your eigenvalues, right? Those are your eigenvalues for your matrix. Okay, let's come back over here. What we have to do now is find the corresponding eigenvectors. So you have to actually consider both of these lambdas, right? To find, it says find all of the bases for all of the eigenspaces here. So I'm going to do that. Let's start with lambda equals 4. It doesn't matter which one you start with at this point. Later on, there may be a reason to prefer one over the other, but at this point, we'll just pick lambda equals 4 first. What I have to do is I have to look at the null space. I'm going to take the null space of the matrix that I get by subtracting 4 from the main diagonal of A. So we come back over to the matrix A and we subtract 4 from the main diagonal. So that creates this matrix here. Okay, so I subtracted 4 from the main diagonal of that matrix. Now, the thing is, this matrix has to be not invertible, right? Remember that we set the determinant equal to 0 over here. That means the matrix is not invertible. So we are not surprised that this matrix doesn't look invertible, right? It's got a row of zeros in it. Now, later on, we're going to see some examples where it's not quite as obvious that the matrix is not invertible, but you have to trust the theory The theory says that these null space matrices that you are writing down in this chapter are always not invertible, which means you can always basically cross off a row of the matrix, right? If a matrix is not invertible, then if you row reduced it, you'd get a row of zeros. Here, we already have that row of zeros, so we don't have to do anything. But in general, it may not be quite as obvious, but you will know from the theory that you have to be able to cross off a row, okay? And I don't mind, you can just draw a line through it, perfectly fine, okay? Now, we have to row reduce this matrix, right? Just row reduce the matrix. If we do that, we're probably just gonna multiply the first row by 1/2, right? And now at this point, you know, we have our variables x and y. I can just let y be a free variable, and then I can just notice that x is going to be 2 times that. Okay, this is back to chapter 2, right? So there you go. And if you want to create a vector out of that, I'm going to draw it as a column. The vector would be 2t and t, right? Just like the old days, this is how we do this. And if we want a basis, well, it's the usual thing. We just have to bust out the variables. In this case, there's just a single variable to bust out. So when I bust out the t, I get a basis, and that basis is 2 and 1. So this is a basis for E sub lambda equals 4. So I'll just write it that way. So the eigenspace corresponding to lambda equals 4, that's what we're looking at here. The basis is just 2 and 1. Easy enough? And that's the vector that I had pulled out of a hat, right? When we first did that example a little bit ago. Okay, now we have another eigenvalue to do. I'm going to go ahead and erase this determinant calculation here so that I have room to write the next part of it. Lambda equals 6. Lambda equals 6. In this case, we're going to be looking at the null space. The null space of the matrix that we get when we subtract 6 from the main diagonal of this 2 by 2 matrix A. So when I subtract 6 from the main diagonal, I'm going to get this matrix right here. So I've subtracted 6 from the matrix A along the main diagonal. Again, that matrix has to be not invertible. We can clearly see that. And in fact, you can see that the 2 rows are multiples of each other. So you can just cross one off if you want. And if you row reduce this one, you're going to end up with something like that, basically, right? 0 with a 1 on the top row with a pivot, and then a row of zeros at the bottom. So if we were to solve this system for x and y, so again, I have x and y as my 2 variables. Notice that y has to be 0, because this is 1 times y equals 0 in the first row. But there's no pivot in the x column, so x is free. X is just equal to t. And I can already see that my basis for E sub lambda equals 6 would just be, what would it be? It would just be 1, 0. After you bust out the t, that's going to be your basis. Okay? All right. Does that make sense to everybody? We have 2 eigenspaces here, one for each of the lambdas, and both of those eigenspaces were one-dimensional. Okay, we're going to start to care about the dimensions of these eigenspaces a little bit more as we go on. Okay. Actually, this is not a bad time for me to mention something that you might have noticed here. Do you notice the original matrix A in this example is actually upper triangular? Right? It's an upper triangular matrix. I would just like to say a quick word about that because there's something sort of general that we can say about that. So, you know, I'll just state this as a fact, and then I think you'll be able to understand this fact pretty easily. If capital A, which is still n by n, is upper or lower triangular. If we have a triangular matrix, like this one that we just started with right here, if we have a triangular matrix, so you have to remember what upper or lower triangular means, but if we have an upper or a lower triangular matrix, here's the deal, guys. The eigenvalues are right on the main diagonal of the matrix. In this case, 6 and 4, right? Those were the lambdas, right? So in this case, the eigenvalues of A lie along the main diagonal. There we go. For a triangular matrix, the eigenvalues will always lie along the main diagonal of the matrix. This gets to be useful and important when you're asked to create an example of something. Let's suppose I ask you to create a matrix that has a certain set of eigenvalues. Say I want a matrix that has eigenvalues 3, 7, and 10, right? Well, what you can do is just make a triangular matrix whose diagonal entries are 3, 7, and 10. Okay, so, and you'll know without having to do a whole lot of work that is in fact the eigenvalues for that matrix, right? So this is just a handy fact for creating examples, right, that have certain eigenvalues that go with them. Do you see why this fact is going to be true? Right, you might remember that for a...
I had a connection problem. So
Jonathan, are you good?
I'm good. I had a connection problem.
Okay, no worries. Okay, so do you see why this fact is going to be true? It's because when you have a triangular matrix, how do you find the determinant of a triangular matrix? Well, you just multiply the main diagonal, right? It's exactly what we did when we found the determinant of this matrix. Actually, it was the determinant of this matrix minus lambda I, right? We got 6 minus lambda times 4 minus lambda, right? It was upper triangular, so 6 minus lambda times 4 minus lambda. And so the lambdas are just 6 and 4. It works the same way for any triangular matrix. Okay, now I have another set of fun facts that I'm going to just tell you right now. When I used to teach this class, I didn't really go over these fun facts so much, but it turns out they are really handy. So I'm going to just tell them to you now. The bad part about these fun facts is I'm not going to prove them right now. It's really something better left for Math 307, a little more of a junior level math course in terms of the proofs, but the facts are really cool and really helpful. So I want you guys to know them so you can use them, okay? So these are 2 fun facts about eigenvalues. A couple of fun facts on eigenvalues. Okay, so the first one is if you add up all of the lambdas for your matrix. By the way, if your matrix is n by n, if you have an n by n matrix, you will get n lambdas. Now, some of those lambdas might be repeated values of lambda, but you will always get n lambdas. The fun fact about these lambdas is if you add them together, you always get the trace of your matrix. The trace of your matrix. Do you remember what that was? The trace is just the sum of the main diagonals. You just add up the main diagonals. So in our matrix here, 6, -4, 0, 4, right? The trace is just 6 plus 4, which is 10. And if we add up our lambdas, which were 6 and 4 also, we get 10 as well, right? So this is always true. For any matrix, the lambdas always add up to the trace. Why is that so useful? Well, it's a great way to check that your lambdas are right. Right? I know on the first example I did, it was pretty straightforward, but if you have a larger matrix, maybe the determinant is a little harder to calculate. You could be concerned that you made a mistake and got one of your lambdas wrong, which is, by the way, a very bad thing. You don't want to get your lambdas wrong because it messes everything up that you're going to do with those lambdas later. So a good way to sort of check that you have done your lambdas right is to use this fun fact. If you add up all of your lambdas, it should add up to the trace of your matrix. Okay. The second fun fact is that if instead of adding the lambdas, if you multiply all of your lambdas, so if instead of adding the lambdas, you multiply the lambdas, you will always get the determinant of your matrix, as it turns out. Again, I'm not proving these facts for you right now, okay? I'm going to let you use them because they're really handy for verifying that your lambdas are correct. But the proofs are a little more involved. I would prefer to leave that for another time, for another class probably. But still, it's good to know these facts, okay? Again, guys, don't be shy. If you have questions, just shout out. I've got my volume all the way up here, so I can certainly you know, hear you. If you have a question, just unmute yourself and throw it out there. So this is great stuff. What's on the board right now is great stuff from a theory point of view, right? If you're trying to create examples that have certain lambdas, or if you're trying to check that your lambdas make sense against the fun facts, right? It's pretty easy to do that, okay? Let's go back though, and I would like to do another example of finding the eigenvalues and eigenvectors of a matrix. So I'm gonna start working with some slightly larger examples now, okay? So let's do this one right here. So this is example, another example. Find bases for the eigenspaces of, so here's my matrix. It's going to be a 3 by 3 matrix. We have 3, 0, 0, 0, 2, -1, and 1, -1, 2. Okay. Now, this time, the matrix is not triangular. So I can't just grab the lambdas off of the main diagonal. That would actually be wrong. Okay. So we actually have to go through a little more calculation. I have to do the characteristic equation. So I'm going to find my lambdas by doing that. So for the solution, I'm going to look at the determinant of the matrix that I get by subtracting lambda off of the main diagonal. So when I subtract lambda off of the main diagonal, this is the matrix that I'll get. So I'm just subtracting lambda from the main diagonal of the matrix A. And now I have to find this determinant. Now, here's the thing, guys. This matrix is 3 by 3. It's a little harder to get the determinant, isn't it? Now, you might remember that in chapter 3, we had an arrow method that we learned, right? But it turns out that that arrow method is not going to be so helpful here. Because what you're going to end up getting, you can see the very first diagonal, the main diagonal there, 3 minus lambda times 2 minus lambda times 2 minus lambda. When you expand that out, you're going to get a cubic equation for lambda. Cubic equations are not always easy to solve. So for the most part, guys, in chapter 7, even for a 3 by 3 matrix, the arrow method that we learned that was kind of handy back in chapter 3 is not going to be so useful here, right? Instead, we're going to depend on whoever wrote this question that they made it relatively easy to find the determinant without the arrow method. And you might notice that the first row of the matrix has a lot of zeros in it. So let's expand. Let's do cofactor expansion on that first row. Okay, it's not always going to be the first row, but look for zeros in your matrix, guys, right? Because that's often going to be a good suggestion. So what I'm going to do here is I'm going to expand the first row. Okay, so I'll get 3 minus lambda from this entry here times the determinant of this little 2 by 2 submatrix that I just circled. Now, to do that determinant, I'm just going to use the AD minus BC on that part. So 2 minus lambda times 2 minus lambda, and then minus 1. Okay? So this is a little harder than the first example. If you take that expression that we just wrote down, and if you multiply it out now, then you've lost the advantage of doing cofactor expansion. You do not want to multiply this whole thing out. If you multiply this whole thing out, you'll be left with a cubic equation again, and you'll be stuck struggling to find the roots of that equation. So don't multiply this out. In fact, you want the opposite of that, right? You actually want to totally factor that expression. You want to totally factor this thing. And it's great that the 3 minus lambda is already factored out in front. Now, what about the part in the bigger brackets that I drew? I drew those bigger brackets on purpose to keep it clear in my head what I need to do. That one does not factor immediately, but the part just in brackets is only a quadratic equation, right? Let's just see that. So if you multiply out the part that's in brackets, you're going to get lambda squared minus 4 lambda plus 3. Okay, so that's just multiplying out the part that's in the brackets. And the thing with that is that a quadratic equation isn't so bad to factor. You can use the quadratic formula, for example, or in this case, you can probably just see how it factors. This factors, so I'm going to leave the 3 minus lambda here. This thing actually factors as lambda minus 3 times lambda minus 1. Okay? And so what are my lambdas then? Well, I have, so again, you're setting this equal to 0 eventually, right? Eventually you're setting your characteristic equation equal to 0. So from this first factor, we get lambda equals 3. From the second factor, we get lambda equals 3. And from the third factor, we get lambda equals 1. Notice that we do have 3 lambdas. We do get 3 lambdas out of this. And that includes repeats. Guys, when you have repeats like this, the same lambda more than once, you should definitely write it down more than once. We are going to want to keep track of repeats. When one of my lambdas shows up multiple times as a root in this characteristic equation, I'm going to want to know that. So it is important that you write down the repeats there. Let's check it with the fun facts. If we add up these 3 lambdas, 3 plus 3 plus 1, well, that's 7. What's the trace of the original matrix? The sum of the main diagonal, 3 plus 2 plus 2. That's 7, right? So it works. And similarly, if you multiply these 3 lambdas, 3 times 1 is 9. And if you take the determinant of this original matrix that you were given, you can just cofactor expand, for example, on the first row of that matrix. You're going to quickly get 9 as well. So these lambdas are correct. It's nice to have the fun facts to just check that the lambdas were correct in the first place. Okay, now that's the eigenvalues, but we still have to find the eigenvectors. We're going to have 2 eigenspaces here because we have 2 lambdas. For reasons that are going to become clear very soon, whenever you have a repeated lambda, the same lambda coming up more than once, you are going to always want to start with that one in terms of doing your eigenspaces. So I'm going to come over here. I'm going to erase my fun facts now. And I'm going to start with lambda equals 3. And I'm going to try to find the corresponding eigenvectors. Lambda equals 3. Okay. So I'm going to do the null space of the matrix that I get when I subtract 3 from the main diagonal. So I'm just subtracting 3 from the main diagonal, and there's my matrix. Remember that this matrix can't be invertible, right? You can see a row of zeros already on the top. If you were to do row operations on this, you would end up putting that row of zeros on the bottom, yeah? And you would have a 1 and a -1 and a -1 here, and a 0 and a -1 and actually, and the second row you could just multiply through by a -1, so you just get 0, 1, and 1. And then we just circle our pivots, just like we've been doing for quite a number of weeks now. Okay. Notice that you get a free variable, right? You have to. Okay, the matrix is not invertible, so there's going to be something in this null space. So the z variable, we could call that t. If we do that, then by back substitution, y would be equal to negative of t. And then from the first row of the matrix here, right, the first row, you can see that x has to equal y plus z. So x actually has to equal 0. So x minus y minus z has to equal 0. In other words, x is equal to y plus z. Okay, and so my basis, I'm going to try to squeeze it right here if you guys will look closely here at what I'm going to do. I'm going to bust out that t that I see, and I'm going to get 0, -1, and 1 as my basis. Can you guys read that okay? 0, -1, and 1. Okay, so that is my basis in this case for the first eigenspace. By the way, something that I want you to notice is that the lambda equals 3 shows up 2 times right here, but it only produced 1 basis vector. This is something that we're going to be keeping track of very soon. Okay, so we're going to be counting the sort of the multiplicity or the weight of each lambda that we find, how many times that lambda arose in the characteristic equation. In this case, 2 times. We're going to keep track of that multiplicity and compare it with how many basis vectors we get out of the eigenspace. In this case, lambda equals 3 fails to pull its weight. So something to keep track of. Now we can also do the, we can also do the other eigenvalue. Let me come back over here. The other eigenvalue is lambda equals 1. So let me put that one right here. So I'm going to do the null space again. I'm going to do the null space this time. I'm going to subtract 1 from the main diagonal of the original matrix. I'm just subtracting 1 from the main diagonal of the original matrix, okay? And let me find, I think I'm going to just skip the details. You have to row reduce this matrix. Guys, this might be a good example. This matrix right here does not look like, I mean, it looks like it might be invertible. You don't know. But guys, here's the deal. I promise you, I absolutely promise you, if you found the lambda correctly, right, this matrix can't be invertible. What that means is that you know that if you do the EROs, some row is going to get zeroed out. And it turns out you can sort of preempt the calculation and say, look, I can already see that the first 2 rows, if I want, I don't really have to mess with those. So I can just go ahead and cross off the 3rd row. Guys, I'm being so lackadaisical now, right? Back in February, I would have made you show all the EROs every single step, right? And so on and so forth. Now that we've been at this for a while and we sort of understand the theory, I am perfectly okay if you just want to cross that row off on theoretical grounds alone. You have to be able to cross off a row. Now, you didn't have to cross off the third row. The key point is whichever row you cross off, as long as the other two rows are, you know, not multiples of each other, you're good. See, you could get into trouble with this if you're not careful. Suppose you had this matrix. Okay, you don't need to write this. You don't need to write this down. I just want to show you that you do have to be a little careful. Suppose you had that matrix there on the bottom left, and I said, oh, that matrix is not invertible. Go ahead and cross off a row. The trouble with this last matrix is you better not cross off this row, right? If you cross off 3, 4, 5, look what you're left with. You're left with two rows that are multiples of each other again. You should have been crossing one of those off. So in a matrix like this, it's important to be careful that you can't just randomly cross off any row that you like. You know that some row will cross off, but just be a little cautious about it. This is a perfectly safe thing to do in this matrix because I can see that the first two rows are not multiples of each other, okay? Now, how is the rest of this going to go? Well, I'm going to have, you know, z is going to be my free variable again, the third column, right? So x, y, z here. So z is equal to t. Therefore, from the middle equation here, y minus z equals 0. So y is equal to t. And notice that x has to be 0. Because on the first row, 2 times x plus nothing equals nothing. So that means x is 0. And so my basis in this case, after I bust out the t that I have there, my basis would be 0, 1, and 1. All right? Good enough so far? Okay, let me see here. While I'm coming along, I just want to check. Yeah, let me do one more example, and then we're just going to take a short break, okay? As I mentioned, I'm going to try to take a short break in the middle, but let me do one more example first, okay? Let me write the example down here in the bottom right corner of my whiteboard. Find bases for the eigenspaces of, so I'm going to give you another matrix here. This is going to be the matrix 2, negative 13, 1, and 6. Okay. So this is just a 2 by 2. So it looks like this would be a pretty easy problem, but something interesting happens. So this is why I want to do this real fast, okay? So for the solution, I'm going to do my characteristic equation like usual. I'm going to subtract lambda off of the main diagonal of this matrix. Okay, and because this is a 2 by 2, I don't mind just using the 2 by 2 determinant formula. So I'm just going to get the quantity 2 minus lambda times 6 minus lambda, and then plus 13. It'll look like that. And if you, see, in this case, I don't mind multiplying it out. Right? On that 3 by 3 example that we did a minute ago, I didn't want to like totally multiply out the characteristic equation because I wasn't sure if I'd be able to factor a cubic. Here, I know I'm only going to get a quadratic because it's a 2 by 2 matrix. The highest lambda power that I'm going to have is lambda squared. And I know that I'll be able to factor a lambda squared equation. So I don't mind multiplying this one out. I would just get lambda squared minus 8 lambda plus 25. And that is what I have to set equal to 0. Okay, so this is my characteristic equation. I'm just going to put a box around it there. That's my characteristic equation. Now, that does factor. It just doesn't factor nicely, right? Every polynomial will always factor, but the issue here is that it doesn't have a nice factorization like our earlier examples. So what are you going to go to if you're trying to find the roots of a quadratic equation, right? We're going to be needing this, by the way, for most of the rest of the semester. The quadratic formula starts to become really important. So if I use my quadratic formula here, you know, the negative b plus or minus the square root of b squared minus 4ac all over 2a, I'm going to get something like this. 8 plus or minus 64 minus 100 all over 2. And 8 divided by 2 is 4. And here we see something interesting happening with this radical. 64 minus 100 is negative 36. The square root of negative 36, okay, it's square root of negative numbers, right? Means we have to use the imaginary I to handle this. The square root of negative 36 is actually 6i. And then I'm dividing that by 2 because the whole thing was over 2. So 6i over 2 is just 3i. My lambdas are 4 plus or minus 3i. Okay, now let me just make sure that those lambdas are reasonable. By the way, so in other words, I have a lambda of 4 plus 3i. And then I have another lambda of 4 minus 3i. Let me just give myself room here. Let's check those lambdas with the fun facts. If we add those two lambdas together, 4 plus 3i, add that to 4 minus 3i, the imaginary parts cancel out. It adds up to 8, right? The two lambdas added together adds up to 8. Look at your original matrix down there in the lower right corner. The trace, right? The trace of that matrix is 2 plus 6, which is 8. It works. Okay. Similarly, if you multiply 4 plus 3i times 4 minus 3i, if you multiply those two complex numbers together, you're going to get 25, which is the determinant of A, right? So that's always a good thing to do, guys. You want to check that your lambdas are correct, because otherwise when you start doing your null spaces and everything else, it's going to be filled with mistakes, right? So you really want to get these lambdas right. Okay, so let's take a look at the top, at the first one up here. Let's do the null space of this first eigenvalue. I have to subtract. Now be careful with this. We now have complex numbers involved. That's why I'm doing this example, if you haven't figured that out by now. I wanted to show you complex numbers because they do come up. So I'm going to subtract 4 plus 3i from the main diagonal of A. Let's see what we get. So if we subtract 4 plus 3i, I'm going to end up getting negative 2 minus 3i, and then negative 13 stays the same, 1 stays the same, and then I have 6, and I'm subtracting 4 plus 3i, that would be 2 minus 3i. Okay. Now, guys, here's where my little comment about how you have to be able to cross off a row is really huge. You really don't want to do EROs with this kind of a matrix with all the imaginary numbers that are in it. It's going to be messy. The fact of the matter is, though, you don't have to do any EROs here at all, right? What we can do is we can just trust the theory. The theory tells us that this matrix can't be invertible. In other words, this theory tells us that those two rows must be multiples of each other. The trouble is that this imaginary number I sort of hides the fact that those two rows are multiples of each other. It's not so obvious that they are, but they have to be. These rows have to be multiples of each other. So here's what I'm going to do. I'm just going to cross off one of the rows. I know that if I trust the theory and do the EROs, one of these rows has to get zeroed out. It does not matter which row you cross off. In this case, you only have two rows. I will usually cross off the one that looks maybe slightly messier, if there is such a thing. So there you go. So there's my matrix. I only have one row left. Here's my pivot right here. Okay. Now, here is another, well, so what I can do here is I can say, all right, so I'm going to let y equal t. And then when I solve for x, so what are we going to have here? X plus 2 minus 3i times t equals 0. So x would just be negative of 2 minus 3i times t. And so my basis, nothing wrong with imaginary numbers being in this answer. My basis is just going to be negative of 2 minus 3i and 1. Okay, I hope you guys can see that all right there. Negative of the quantity 2 minus 3i, comma 1. That's a 1 right there. Okay. So that is for the first eigenspace. Okay. Is everybody with me? I just crossed off one of the rows of that matrix right there. I just crossed off one of the rows. I know I have to be able to do that. Okay. Now, I know that this seems kind of messy to deal with these complex numbers, but there is one piece of good news here, which is that when you then go to your other lambda, by the way, these lambdas, these complex lambdas, do you notice that they are just conjugates of each other? We have 4 plus 3i and we have 4 minus 3i. It turns out that you don't have to go back and do the other lambda from scratch in this complex numbers case. What you can do is you can go right to the basis. Actually, you know what I want to do? I want to come over here to this basis and I want to write it one more time. I'm going to actually factor the minus sign through. So negative 2 plus 3i and 1. I just want to do that. It'll make this thing, it'll make my next step a little more obvious. So I've just put the minus sign through the first slot there. Now, here's the cool thing about this other eigenvalue. It turns out that when you have this complex pair of eigenvalues like we have, that you can immediately write down the basis for this one, right? And all you have to do, as it turns out, this is just going to save you some work. All you have to do is conjugate your answer for that basis. So you already did the work to find this basis, so we can write down this basis without even taking a breath. How do we do it? We just conjugate. So all I'm going to do here is I'm going to conjugate the first basis to write down the second basic. So the conjugate of 4 plus 3i is 4 minus 3i. All you're doing is you're switching the sign of the imaginary part of your eigenvalue. And that's the exact same thing you're going to do here. You're going to switch the sign of your entries in your basis. So this is going to become negative 2 minus 3i. So we had negative 2 plus 3i. Now I'm going to write negative 2 minus 3i. When you conjugate a real number like 1, it doesn't change. Only the stuff that's attached to an I has a sign change. So the second slot is still a 1, but the first slot in the basis is negative 2 minus 3i. This is not a hard thing to prove. I don't really want to do it right now because it's not that interesting or insightful. But if you were to actually go back and actually work out, you know, lambda equals 4 minus 3i and go through the whole null space thing again, you would come up with that exact basis that I just wrote down. Okay. So just a quick tip, you can get complex numbers when you're finding your lambdas. And if you have complex eigenvalues, then you're going to get complex eigenvectors as well. And the nice thing is, once you've done one of your eigenvalues and found its basis, the other one kind of comes for free. You don't have to work quite so hard. Okay? Does anybody have any questions on this example? Because complex numbers are going to be coming up a little bit more often kind of from here on out. Okay, I tell you what, let's take, according to my timekeeper here on my computer, it says it's about 1:12 right now. Why don't we take just a short break until 1:20? And that'll give me a chance to rest my voice. If you need to use a restroom, take a quick little break yourself. Feel free to do that. When we come back from the break, I'm going to open up the homework with you. We're going to go back. We can look at some of the homework from section 6.3 and 6.4. So you might want to dig that up. And then I also sent you by email yesterday a group work number 10. So you might see if you can dig that up as well, because we're going to do that when we come back from the break. We only have about 30 minutes to go. So when we come back from the break, we'll do those two things, homework questions and a little bit of group work. It's all going to be the chapter 6 stuff. I'll come back to this on Thursday, this material. I've already covered everything that you need to be able to do Thursday's homework from section 7.1. It's not a very long assignment, by the way. So we'll call it good on chapter 7 for now. And we'll finish the last 30 minutes today on chapter 6. Okay, so go ahead and take a break, and I'll be back in about 6 or 7 minutes. Okay, thanks. Actually, if you have questions on the homework, you could just write them into the chat, into the Zoom chat, and then I'll know kind of what problems you're thinking you want to look at. All right. Well, I hope that you guys are still hearing me and able to watch what's going on behind me. It looks like pretty much everybody's still here. I think these little breaks in the middle are going to be good for me, at least. It's a little physically challenging for me, kind of in front of this setup that I've got, but it hopefully is working okay. I hope you guys can see and hear everything really well. Tonight we have a homework assignment that's due. It is homework number 16. You should have gotten a Dropbox invite to share your files with a folder for this homework, and please do turn that in by the end of the day today. 11 p.m. Is sort of what I usually shoot for, and then I'll put my grader to work on those for you. In the meantime, does anybody want to ask me any questions about the homework that's coming in today? Okay, so I see 6.3 number 9 has been mentioned. Let me take a look at that. It's asking to find the kernel and range of a transformation. So the kernel and the range. So this would be a good chance for us to review what that means. And what it says is to use the linear transformation in problem 28 of section 6.1. So let me pull that one up. So in problem 28 of section 6.1, what we were given is that our transformation sends the vector 1, 0, 0, 0 to 3, -2. And then it sends the vector 1, 1, 0, 0 to 5, 1. And then it sends the vector 1, 1, 1, 0 over to -1, 0. And finally, the vector t of 1, 1, 1, 1 is equal to 2, 2. Okay. By the way, as you can obviously tell, this is a transformation. This is a transformation that goes from R4 to R2, right? You can see that because the inputs have 4 slots and the outputs have 2 slots, right? So in this case, where we have a transformation from Rn to Rm, please remember from before spring break that any transformation like this can be represented as a matrix. And to do this problem, it's going to be good to figure out what that matrix is. The size of the matrix, I'll call it capital A up here. The size of the matrix is 2 by 4. It's going to be a 2 by 4 matrix, right? And how do you fill out this matrix? So this kind of goes back to what we've been talking about before. Sorry, I'm just making sure that everybody's in the room that wants to be here. So this is a 2 by 4 matrix. The way that you fill out this matrix is you do it column by column, right? The first column of this matrix should just be T of 1, 0, 0, 0, which was actually given to us. It's just 3 and -2. So that's the first column of the matrix that represents this linear transformation. For the second column, we have to write down T of 0, 1, 0, 0. Now, you might notice that in this information here, they did not tell us what T of 0, 1, 0, 0 is. But we can get it from this information. If you look at the first 2 pieces of information there, you might notice that on the left side, if you were to subtract, if you take 1, 1, 0, 0, and you subtract 1, 0, 0, 0, you'll get exactly 0, 1, 0, 0. So in other words, T of 0, 1, 0, 0 is just the second line minus the first line. So that's going to be 5, 1 minus 3, negative 2. And when you simplify that, you just get 2, 3. So that becomes the second column of the matrix capital A. Okay, so again, stop me if there's any questions. This is actually going back to section 6.1. What we're doing so far is just a review of the earlier material. The third column of the matrix should be T of 0, 0, 1, 0. And you'll quickly notice that that's just the third line minus the second line. If you take the third line minus the second line, you're going to get negative 6 and negative 1. Okay? And then finally, T of 0, 0, 0, 1 is just the fourth line minus the third line. And that is just 3, 2. Okay? So this is the matrix for this linear transformation. Remember, we only do this. We only build this matrix if our transformation goes from Rn to Rm. We shouldn't be doing this on every single problem, right? If our problem involves polynomials, for example, you're not going to be writing down a matrix like this. But in this case, when you do have a matrix that represents your transformation, it's easy to get the kernel and the range. If you watched my videos, which I hope you did, you already know that the kernel of T is just the null space of the matrix. And the range of T is just the column space of the matrix. So this is a nice thing to try to understand, right? The kernel of this type of transformation is just the null space of this matrix. So we're just going to, to find the null space or the column space for that matter, we just have to row reduce this matrix. So what I'm going to do is I'm going to just add the second row to the first row here so that I can get a 1 in the upper left corner. So I get 1, 5, negative 7, and 5, negative 2, 3, negative 1, and 2. And now I'm going to take the first row times 2 and add it to the second row. So we get 1, 5, negative 7, 5. And when I take 2 times the first row and add it to the second row, I'm going to get 0, 13, negative 15, I believe, and 12. Okay, so I'm just row reducing the matrix. And this is basically going to be your row echelon form at that point. That's basically your row echelon form, more or less. Technically, we need to divide the second row by 13 to get a pivot in that second row. Maybe I'll do that really fast. So I guess the numbers come out a little bit messy here. So if you divide through by 13, you'll get 1, negative 15 13ths, and 12 13ths in that last row. If I did this right. It's always possible that I made a little goof, but I think I'm okay. Okay? So I've got pivots now, and so then we just have to set up free variables and solve for this null space. So let me just come over here again really fast. If I just label my columns with 4 variables here, x, y, z, and w, then of course you can see that z and w are the free variables, right? So I could just let z be equal to t, and I could let w be equal to r. And then I've got to solve for y and then for x, right? So y would be, if I move things around on that second row, I think y is going to be 15 13ths of t minus 12 13ths of r. Okay, this would be what y is equal to. And then I've got to figure out what x is. This is kind of messy. I don't have my solutions in front of me. But I think I'm going to let you guys finish this calculation. just because it's too messy for me to do just in this little board space. The point will be that you're going to bust out the variables. You know, you're going to bust out these variables, and there are two variables to bust out. So this is a basis for the kernel of T right now. When I bust out the R, I'm going to get something here, and then -12/13, 0, and 1. And when I bust out the T, I'm going to get something there, 15/13, 1, and 0. Okay. Now, in the back of the book, they might have multiplied through by 13 just to clear the denominators out of it. So keep that in mind, that you can have more than one answer. But that's basically what it is. You just need to figure out what X is using the first row of the matrix on the right-hand side. So far, so good. This is the kernel of T. We just find the null space of the matrix and go from there. Okay, what about the range of T? Well, the range of T is just the column space of the matrix. And you notice that we already row reduced the matrix on the right-hand side over here. It's the first two columns that have pivots. So remember how you get your basis for your column space? You just go back to the original matrix and grab the corresponding columns from the original matrix. So this one is easy. The basis for the range of T, I'll put it up here. Basis for the range of T is just going to be the first two columns of A. Okay? Remember that in this problem, right, T is a transformation from R4 to R2. And that's why we got a 2x4 matrix representation. I also want to remind you, this is a great chance for me to remind you, the general rank nullity theorem, which you guys should have watched the video on already, tells us that the dimension of the kernel plus the dimension of the range, which is really just like the nullity plus the rank, if you think about it, has to add up to the dimension of V. So the original vector space R4, right, that's 4-dimensional. So here we have a 2-dimensional kernel and a 2-dimensional range. 2 plus 2 gives us the 4, right? So that all more or less makes sense. Okay, so for the purposes of a transformation from Rn to Rm, it all comes down to finding this matrix. Every single time you want to write down that matrix, row reduce it, and then find your basis for either your null space or your column space. Okay. Any questions so far?
Wait, Professor?
Yes.
Can you repeat that again? My computer lagged for a moment and it missed you.
All I said was that I was just reviewing the general rank nullity theorem, which isn't what's asked for here in this problem, but just the point being that we have a 2-dimensional kernel, we have a 2-dimensional range, and 2 plus 2 gives us the dimension of V, right up here on the upper left, which was 4. So this is all content from the videos that you guys watched, I think, before class, okay? Okay, does anybody else have any questions on the homework for today? I'll also remind you that I'm going to be in my Zoom office hours later on today. I do have another class to teach at 4 o'clock until 5:15. But other than that, I'm going to be around kind of in my laptop on the background. I actually have been having I'm in my office a lot because I leave my computer on and I just sort of leave the office hour room open quite frequently. So feel free to drop in there. Just make sure you're going into the office hour Zoom ID number rather than this number that we're in right now for the class. So, Okay, I'm going to trust you guys that the homework is relatively good for now. If there are more questions, stop by my office hours later and we can take a look at that. What I would like to do next is talk about the group work that I had passed out or that I had emailed you yesterday. So I'm going to go ahead and do that. Let me erase the board here. If you could pull out that group work, that would be super. I'll write the problems on the board again, just in case you don't have it with you. But if you do have it, you'll be able to look at it really easily. These group work problems, guys, are you know, very similar to the types of questions I would put on a midterm. So you definitely want to pay attention here and make sure you understand the group works. So we have you know, 12 minutes here, 13 minutes to try to go through group work number 10. So let me, there's just two problems here on this group work. Let's just look at them together really quickly. Group work number 10, and I'm going to look at the first problem. It says, determine whether the given linear transformation is one-to-one, onto, both, or neither. So what I'm going to, that's a very standard question that you'll definitely see me asking on a regular basis. Let me write down the question first, and then I'm going to remind you what one-to-one and onto means, okay? So let's suppose that we have a transformation on problem number 1 that goes from R4 over to W, and W is given in the question is the set of 2 by 2 symmetric matrices. The 2 by 2 symmetric matrices. Can you guys all see that? Just make sure that I didn't get cut off too badly there. Okay, great. So that's what we have. And the formula for the transformation is, so we give you the formula here, T of A, B, C, D equals, and the formula is the following. We have B plus C. We have B minus 2C. B minus 2C, and in the lower right corner, A minus B plus C. Okay, great. So the question is asking whether this transformation is one-to-one, onto, both, or neither. This is a great chance for me to quickly review what those concepts mean, okay? So let me just do that, I'll just steal a little space here to remind you here. T one-to-one, I usually write that as 1-1. It just means that the kernel of T is just 0. So a one-to-one transformation, just to review from section 6.4, which is on those videos that you watched, one-to-one transformations just have a trivial kernel. Kernel is just 0, okay? And the other concept is onto. T being onto just means that the range of T is the whole entire space W. Okay, so these are just definitions, but they're very, very important for being able to understand section 6.4. Okay, now there is a little bit of information that is worth memorizing. Guys, this is going to be on the next midterm for sure. I know it's a month away from now, but this is a great time to sort of try to get this piece of it down. So not only do you need to know these definitions, but there's another piece of the puzzle here that we can also fill in, which is that there's sort of 3 cases, right? There's the dimension of V might be bigger than the dimension of W. And then that tells us something. Another possibility is that the dimension of V would be less than the dimension of W. And that would tell us something. I'm going to come back and fill this in a minute. And then the last case would be that the dimensions are actually the same. So the dimension of V might be equal to the dimension of W. Now, so let me, hopefully this is coming across on the screen okay for you guys. There's 3 scenarios here. When you have a transformation from V to W, either V is bigger than W, smaller than W, or the same size as W, right? That's what the dimension is kind of measuring. If V is bigger than W, right? If the domain V is bigger than W, then T can't be 1-to-1. It cannot be. It might be onto, but it cannot be 1-to-1 in that case. All right. The opposite thing happens in the second case. If V is smaller than W, then T can't be onto. Okay, so if V is smaller than W, there's no chance that T could be onto. And finally, if V and W are the same size, then T is, in this case, T is either both or neither. Both or neither. So if it is 1-to-1, then yes, it will also be onto. If it's not 1-to-1, then it won't be onto. Okay? So the point that I'm making with this little explanation in the middle is that if you know the dimension of V and the dimension of W, then when you run across a question like this, where I'm asking is T 1-to-1, onto, both, or neither, you'll be able to rule some things out right away. Yeah, because you can just compare the numbers and make that decision. Let's look at this problem. R4 to W. What's the dimension of R4? Just 4, right? So the dimension of V is 4 in this case. What about W? What's the dimension of the 2x2 symmetric matrices? It's a little bit of a trick question, so you have to be careful because I'm not talking about all 2x2 matrices. I'm only talking about the symmetric ones. So if I was looking at how a 2x2 symmetric matrix would look, how would it look? Well, you'd have any number in the upper left corner. This is the form of this matrix, right? You could put any letter in the upper right corner, but you'd have to put that same letter in the lower left corner. So the B and the B have to be the same here for a symmetric matrix. So we have A, B, B, and C. And when you bust out those variables to get a basis, right, you see that the dimension of W is 3. So on this problem, the dimension of V is 4. That's R4. But the dimension of W is only 3. Because W is not all 2x2 matrices. This is the tricky part of it. W is just the symmetric 2x2 matrices. So here's our problem. We have a 4-dimensional vector space V mapping to a 3-dimensional space W. V is bigger than W, so that's this scenario right here, right? T cannot be 1-to-1. Okay, T cannot be 1-to-1. So that means it's either onto or neither. So the question is T 1-to-1, onto, both, or neither? And at this point, we know that T cannot be 1-to-1 or both. I haven't had to do any work yet. All I had to do is figure out what's the dimensions of my 2 spaces. This is fast, right? We can get this easily. And then it's going to cross off 2 out of the 4 choices just right off the top before we have to do any work. Now, they are asking us whether T is onto. And for that, it's a maybe at this point, right? We're not going to get a fast answer for that part of it. We actually have to think about whether this is really going to be onto or not. Here's the definition of onto over here. We need to look at the range of t to sort of figure that out. So let me erase something. Let me look at the, let me just actually erase this whole thing. Remember, this is all being recorded, so you guys will be able to look back at this later. But let's look at the range of t. Let me just remind you that for the range of t, this is the formula. It's the span. This is coming from the videos, right, that you've already watched. It's the span of a transformation of a basis of R4. So you need to think about a basis for R4. Well, you can choose any basis you want when you're doing this span equation, but you should probably pick something that's pretty easy, like 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Like I would do it that way. Take the span of those, of the transformation of those 4 vectors. So we actually have to take a minute now. Okay, we'll just finish this up. It won't take too long here. Okay, we actually have to make sure that we can transform these 4 things. Make sure you know how to do that using, we're going to use this formula right here. Okay? So the deal is, what is t of 1, 0, 0, 0? Well, if we look at it, we're going to put a 1 for A, a 0 for B, a 0 for C, and a 0 for D. If I want to know what t of 1, 0, 0, 0 is, those are the values. So plug those values where you see the matrix. We're going to get a matrix here, right? What matrix is this going to be? We're going to get a 0, 0, 0, and 1. So I put a 1 everywhere I saw the A, and I put a 0 everywhere I saw a B or a C or a D. Okay? Let's do the next one, t of 0, 1, 0, 0. So this time I'm going to put a 1 for the B variable, and I'm going to make everything else 0. Okay? So t of 0, 1, 0, 0, I put a 1 for the B variable. I get a 1, a 1, a 1, and a minus 1. Okay? The next thing I need to do is put a 1 for the C variable, right? T of 0, 0, 1, 0, I put a 1 everywhere I see a C. In the upper right and lower left corner here, it becomes a minus 2. So a 1 everywhere I see a C. And then finally, t of 0, 0, 0, 1, I'm going to put a 1 everywhere I see a D, and I'm going to put zeros for everything else. Well, that actually zeroes out that matrix. Okay? So there is the range of t. And the question is, what is that? Like, is that all of W? Does the range of t equal W or not? Well, first of all, the last matrix over here, you can kind of throw it away. It doesn't span anything. The question is, do these 3 matrices span W, the 2 by 2 symmetric matrices? There's 3 of them, and the dimension of W is 3. But remember that we have to make sure that these 3 vectors really do span the space. And so that takes a little bit more work. What you can do is just check if these matrices are linearly independent. Okay, so we've done this many times before, where you lay the matrices out into the columns of a matrix. So each matrix just fills up 1 column, and this would be that matrix, right? You would just build that matrix. The first matrix goes into the first column. Second matrix goes into the second column. The third matrix goes into the third column, right? And now you just have to do EROs on this thing. And I'm just going to save you the trouble. You can clearly see that you can cross off the third row because it's the same as the second row. By the way, don't cross off both of those rows. I've seen people do that before. Just cross off one of those 2 rows. All right, and then I'm just going to save you the headache. I'm going to just tell you that basically you are going to, when you row reduce it, you are in fact going to get pivots going all the way down the diagonal. And that means that there's no free variables. And that means that these matrices, they are in fact Li. So there's 3 of them here, right? 3 linearly independent vectors. They're going to span a full 3-dimensional space. So the range of T in this case is going to equal, this is going to equal W. And that means that we do in fact have an onto transformation. Okay? By the way, one last thing and then we're going to call it a day. Let's say you didn't want to figure all this out right here. You know what you could do? There's another thing you could have done instead. You could have said, you know what? Instead of figuring out the range, I'm going to figure out the kernel. We could have said, you know what? Let's figure out the kernel of this thing. How do you find the kernel? Well, what you do is you set this thing over here equal to 0, 0, 0, 0, right? And then you solve. So to find the kernel, you set the transformation equal to 0, and then this creates 4 equations up here, right? The upper left corner makes an equation, the upper right makes an equation, lower left, lower right. You get 4 equations that you can then solve to figure out the kernel. Now, why would you do that? The kernel has to do with 1-to-1, I thought. The thing is, if you figure out the dimension of the kernel, remember that this general rank nullity theorem, I cannot sing its praises loudly enough. If you figure out the dimension of the kernel of T, then from that general rank nullity theorem, remember the dimension of the kernel plus the dimension of the range has to add up to the dimension of V, which is 4. So if you did the kernel, and you figured it out that it was 1-dimensional, right? Then you would already know that the range is 3-dimensional because 1 plus 3 would add up to 4. As soon as you know that the range is 3-dimensional, well, then you know that T is onto, because take a look at W. W is 3-dimensional. So if your range was the full 3 dimensions, then you would know that T is onto. So all I'm saying is you can get these answers through the back door. If you don't want to actually do the range, fine. Do the kernel instead. Use the dimension of that to then find the dimension of the range, which can then answer this question. Okay. That's about all I've got. Does anybody have any questions on that? Okay, well, we're pretty much out of time for today. There is a second problem on that group work I should mention. I would definitely recommend, I may not have time to go over it. I definitely recommend that you try it. And that just is extra practice in addition to the homework. But that's all I've got for today, guys. Thank you guys so much for being here. I'll be back here again Thursday at noon to continue chapter 7. And we have homework due on Thursday as well. So I'll take some questions on that if there are any at that point. But that's all I've got for now. I'm going to let you guys go. Thanks again for all your hard work and for putting up with this crazy virtual teaching and learning. I hope it's going all right. And I'll see you guys again. I'll see you guys again either in office hours or on Thursday. I'm going to go ahead and end our meeting. Have a great day, everybody. Take care.